My name is Włodzimierz Zadrożny. I work for IBM Research at the T.J. Watson Research Center, and I'm going to be talking about natural language processing and its applications. I will try to make it relatively easy to understand, but of course there will be some mathematics involved, and we will cover quite a bit of the material. So now let's see if we can get to the next slide. Yes. So these lectures will focus on core topics of building natural language applications, and we will try to answer several questions, which are, what is NLP and why is text and speech processing difficult? What are the tools that we can use and do they work? We will talk quite a bit about text preprocessing because this text preprocessing is important for improving the quality of applications. We will also discuss connections with information retrieval, speech processing, and other subdisciplines of the artificial intelligence. And we will talk about promising technologies, including the IBM Deep QA technology, deep question answering technology, also known as Watson. That was the technology that was developed in the project that I was part of, and it is known for competing successfully in the TV game called Jeopardy, where the objective of the game is to answer some questions, sometimes very difficult factoid types of questions, but also puzzles, cultural type of questions, proverbs, puns, and so on and so forth. So it is sort of understood as one of the tests for intelligence. So what it is that we're going to talk about today? Okay, so I want to start with some very easy applications that show the potential of using language technologies, but the underlying text processing mechanism is relatively simple, which is counting of words. Then we will progress to something somewhat more difficult. That is, we will talk a little bit about statistical language processing. And the reason for that is that the technologies that underlie statistical language processing that were developed mostly in the late 80s and early 90s, and mostly at IBM, are very important for today's language processing in general, for information retrieval, and some of them were, or similar types of technologies were also used in the Watson project. At some point, which is probably going to be in 2 or 3 days, we will do a review of Watson architecture, and we'll go more deeply into the language processing pipeline of the Watson project. But to do so, we need all these preliminaries. So today, and probably most of the day tomorrow, will be about those preliminaries. Okay, so we will talk first about what is NLP, what is computational linguistics, so something about the vocabulary, what has changed in the last 20 years, and why we should care. And we'll try to summarize the state of the art. So this will be the first, more or less, 45 minutes. So what is natural language processing? It's a discipline that is concerned with the interaction between the computer and a human using natural language. Okay, so it's not like games, it's about talking to the machine, or typing to the machine, or machine understanding something that has already been written. There are some important areas that we will need to cover, and these are parsing, which is dividing a sentence into various phrases, okay, so into parts, and these parts usually have some associated meanings. Semantics, which deals with meanings. There is sort of on a different axis we can divide into question answering, dialogue, machine translations. This is more like applications, but also language understanding and language processing is important for speech recognition, and this is the topic that we will not cover. What you see on the right here is essentially a collection of words that are associated with this topic, natural language processing. You can build these kind of maps by going to the URL, I think, called word.li, and you can build diagrams, for a web page or for some corpus collection, if you choose to do so. Okay, now there is another synonymous word which is called computational linguistics, and this is again from Wikipedia. The definition is that it's a field dealing with statistical or rule-based modeling of natural language from a computational perspective. So here it's more about how do we model the language. It's not about the interaction, but in practice computational linguistics and natural language processing are really synonymous, and we also have certain collection of sub areas here. Okay, so we didn't have morphology before, so this is about how words are put together from pieces. It's very important, say in Polish. It's less important in English. Polish has a very rich morphology. English, the morphology is relatively poor. Okay, so for instance, plural formation in English is relatively simple. You just add an S at the end in most of the cases. So that would be an example of morphology. Parsing and syntax, this is about parts of speech. We will cover it, maybe we will start today. We talked about semantics and meaning, dialogue, language translation. So these are all the same parts that we had on the previous slide. What you see on the right is an important book that was published, I think, somewhere in the mid-90s. The author of the book is Eugene Charniak, a professor at Brown University in Rhode Island, in Providence, Rhode Island. And essentially what this book does, it combines statistical language techniques, which we will discuss in more detail later today, with the traditional approach to linguistics that involves building a parse tree, finding parts of speech, dividing a sentence into some meaningful parts. So we will at some point talk about statistical grammars, and that was the topic of this book, although we will not use the book as the textbook for this class. All right, so it is worth mentioning that in 1990s there was a transformation happening in the field of NLP or computational linguistics. So prior 1990s, okay, this field sort of tried to find a relationship between a sentence, okay, written here, and its parse, okay, so some structure of the sentence that you may vaguely see in this parse tree here, and the real situations in the world, like somebody putting on some clothes or, preparing for work or doing something like that, okay? And then around early 90s, mid-90s, an important paper was published which was called The Mathematics of Statistical Machine Translation. It was published by a bunch of IBMers, Peter Brown, Vincent Della Pietra, his brother Stephen Della Pietra, and Bob Mercer. And essentially what the paper was doing, it was saying that the way people have been trying to do machine translation is not right, that is trying to find the meaning and some representation of meaning in one language and then map it into another possible structural representation of meaning in the other language, and then from that meaning generate the sentence in another language, okay, that this method is not promising, okay, and therefore a new method is needed, and this method that they proposed was using some interesting probabilistic techniques associated with the Bayes theorem. So we will talk about it in the course of lectures today. And what you see on the right, okay, is essentially the diagram from the original paper by the Google guys, and this shows sort of the the original architecture of the Google search engine. And I put it here because it is, essentially having access to a lot of text on demand is something that happened because of the internet and because of the access to search engines. And what we have right now is that language processing is very much driven by the demands of search and associated business. Okay, that is, there is a lot of work, for instance, on optimal ad placements. And that some of this work involves trying to understand both the content of the ad and what the user might be looking for, that is trying to assign some meaning to the query. So what happened, okay, as a result of this paper that is written, that's in the box in the middle, is that essentially for a number of years, probably until early 2000, maybe mid 2000, that essentially most of the papers published in the field had to deal with the statistical modeling of natural language. And essentially all the work on rule-based modeling, I wouldn't say that it ceased, but it was definitely more difficult to publish. And what we are seeing now is essentially a synthesis of rule-based modeling with the statistical-based modeling. And in some cases, I mean, we have very good results. But I mean, we have very good results, for instance, both, I mean, in three cases: rule-based grammars, statistical grammars, and a combination of rule-based and statistical grammars. So let's continue. Okay, so this is essentially, what happened. It is important both to understand, why it happened and what it gave us, and to understand, the tools that we developed in the last 20 years. By the way, the authors of that paper went to work for a hedge fund called Renaissance Technologies, which was actually run by a former mathematicians, and they are, as far as we know, extremely rich now by doing a lot of stock trading for the last almost 20 years. So where are we now, and why should anyone care about language processing? Okay, so what's happening? So now I'm going to switch to a little bit of the business perspective, just to give you an idea why we believe that text and language processing is going to be increasing in importance. So there is quite a bit of data generated. Okay, so in the last statistics that I was able to find, and that was at the end of last year, was that about 1,000 exabytes of data were generated in 2010. All kinds of data: medical, financial, game data, news. A lot of this data is text, okay? And we essentially have two ways of interacting with data. One has to do with shapes, okay? So we visualize, okay? And, we can engage in some kind of a dialogue with shapes, yes? So people have been doing that kind of stuff. And the other is words, okay? So we understand, we understand the data through words, either through text itself, or through some kind of a summary or analysis of metadata that is associated with these words. And in both cases, we have data mining and machine learning, because with that amount of data, data has to be somehow summarized. And the way to do it intelligently is to use some machine learning techniques. Another thing that is happening is that the economy is changing, okay? We have digitization of the economy. So what you see here, okay, is this funnel of digits, okay? And this is supposed to be the funnel that sucks, you know, the whole economy, all the economies of the world, okay? But we don't know what's on the other side of this funnel yet, okay? We know that it's gonna be a big transformation, but we do not know how it's gonna end. So, you know, prior to digitization, okay, we were talking about, you know, time equals money, yes, you know, everybody says that, and essentially what it meant is that, say, if you save money and the interest rate is reasonable, relatively high, then, you know, with the percentages and systematic savings, you might get rich, okay? So that was one interpretation, this kind of time series interpretation, yes? Also, you know, if you are efficient and so on and so forth, then, of course, you're gonna make more money than you are if you are inefficient. But it looks like we are, you know, getting into a new metaphor that essentially money depends on your ability to interpret a lot of data in little time. And people can, even with speed reading, can't absorb all the information that's there in the text, okay? And they can't absorb, especially, all the information that's given to them in the numbers. So machines have to do both. They have to help with the interpretation, and in some cases, they're gonna be making some autonomous decision based on this interpretation. So I will not be talking about data mining and dealing with numbers mostly. I will be talking about text analysis, what it is that we need to do to help machine understand the language. So again, the moral of this slide is that we have this digital transformation, okay? The reason, I mean, that we care about this digital transformation is that a lot of it has to do with text, and we need to build tools, you know, to accelerate this digital transformation. And just, you know, on the left, what you see here is this, you know, first page of, I think, first edition of Encyclopedia Britannica. It was interesting that more or less at the same time when I was preparing this slide, sometimes in spring this year, you know, there was the news that essentially Encyclopedia Britannica folded. Okay, so now all the encyclopedias that exist are mostly in the digital format. Okay, although schools still buy, for instance, the World Book Encyclopedia in the United States, because, you know, it's good to have something on paper. All right, so to continue the same topic, that is, you know, where we are. Okay, so this is the assessment from some text analytics conference that happened last year. And essentially, I'm going to read it because I don't know if this is readable. So text is a form of big data. Right now, the hotspot is social media analytics like Facebook and Twitter, where consumer voice opinions. There is a lot of work to do to harness the treasure trove of data and convert it into marketing decisions that grow revenues. A lot of brand management and customer support will get immense value from a large corpus of text pulled from the internet into data warehouse. Okay? This transition from anecdotal decision making to decisions based on trends, okay, will be coming from these huge amounts of text. And here the author predicts that social media analytics will drive text analytics into the mainstreams, and there will be plenty of opportunities to do text analytics and make money there, and some of them are mentioned here, which is fraud detection, risk analysis, healthcare research, government trends analysis, security applications, and so on and so forth. And we have at least 10 years left to do the innovation. I mean, probably more than that. So anyway, so it looks like The field is opening, so if you guys at some point want to do something interesting, there will be plenty of work left in this field in 2, 3, 4, or 10 years. All right, so there is some. Okay, so some highlights. Yes, we are going into a transition from anecdotal decision making to decision making based on trends. Okay, so this is part of this funnel, part of this transformation. And it's going to take time to drive text analytics into the mainstream, and at least 10 years. And there is something about social media analytics. So this is the same slide, except that some of these things are highlighted. So, and we will show an example of a very interesting and simple social media analytics application in a few seconds. All right, so I'm gonna show this application, okay, with the permission of the author, actually. All right, if the machine will let me do it. All right. Okay, let's go back. Open hyperlink, and I hope this is gonna be, you will be able to hear it. Oops. So this is a very interesting study where basically we are talking about an industry which is under a lot of pressure, which is newspapers and media in general, okay? The technology that he used is relatively simple, but it was done in a very interesting way. It combines text analytics and social media analytics as this assessment which appeared before was promising that this to be a good area of research. So let me see if I can make it bigger and play.
Hi, my name is Yuri Lipschitz, and this is my research project at Yahoo Labs. You all know Facebook like and share buttons. In fact, Facebook allows anyone to get the total number of likes for any URL. In this study, I show you some interesting lessons learned from Facebook likes. There are 45 sites in our dataset. For each of them, you can see the total number of likes and the link to the top story. You can also sort our collection by any parameter. New York Times is the overall leader with about 7 million likes over 3 months. These days, many editors believe that publishing frequency is the key. Our data shows the opposite, yet long stories attract the majority of user activity. As you see from our measurements, NPR, Guardian, or Yahoo News can get half of their total engagement by publishing only one story per day. It is very surprising to see what stories are the most liked and shared. In top 40, there are only 4 articles about actual political news and 3 about celebrities. The most common type of hit stories is opinion pieces. Why Chinese mothers ask better is the overall leader with 340,000 likes. Other common themes include lifestyle, photo galleries, interactives, humor, and odd news. Some websites display actual number of page views for every article. In this case, we can calculate what fraction of visitors are tweeting or sharing a particular story. Our measurements show that for every 1,000 visits, there are from 5 to 20 likes and tweets. Now you can guess page views of individual articles that do not show page views. To get the baseline estimate, take the number of likes and multiply it by 100. An example, we know that Chinese mothers article has over 600,000 likes. Multiply it by 100 and you can get an estimate of 30 million page views. Sadly, web articles are basically lost 24 hours after publication. Our measurements show that over 80% of likes happen during the first day. Yahoo News has the sharpest decay of user interest, and gadget articles have the longest lifespan. But even in this case, new content can only be visible for 3 or 4 days. This is a visualization of New York Times headlines. The size of every word corresponds to the number of stories. The color represents the average number of likes received by stories on a given topic. Bright red, a lot of likes, dark blue for the minimum number of see them all. These heat maps can be used as a tool for demand discovery. You can also see what are the most engaging topics at the sites of your competitors. Here we picked a few brands and visualized their coverage at several technology blogs. The stories about Facebook, Apple, Skype, and Kinect are universally popular. Coverage of Amazon, Windows, and Samsung is much less engaging. We can do a similar analysis of topics. Our data shows that keywords how, what, best, and future correlate positively with article success. Search, TV, cloud have negative correlation. Video is highly polarizing. For some sites, video features are among the most popular items on the site. Others, like TechCrunch, still have to learn how to turn the video into an engagement figure. Engagement trends can be computed from different signals. Instead of likes, one can use tweets or upvotes from this chart to show most quotable topics at Hypernews website. Lessons, big stories. The data shows that by writing only one story per day, you can get over half of your total likes. Do you really spend half of your effort on big stories? Promote your best content. If hits disappear after a few hours, most readers will miss them. Medium stories. Majority of articles in our data set see very little engagement. You have to ask yourself, why do I publish something my readers do not care about? Demand analytics. You should really know what are the topics of highest engagement in your area of focus. Social media optimization. At this moment, an average reader of New York Times shares only one story per year. A lot of room for growth here. You can find all rankings, heat maps, and large-size infographics at the website of the study. If you want to get an engagement heat map for your site or have any questions, please contact me by mail or Twitter. This study can be useful for many professionals in news industry.
All right, so let's stop it there. I don't know, I hope this was understandable or otherwise. Okay, so we're gonna go through some details of this study, okay, because I wanna emphasize some points. By the way, the URL that is mentioned there in the video is not working, but if you do Google search on log-like study, you're gonna get it. Okay, so all right, so what happened? Okay, so what did Yuri Lifshitz do here? Okay, well, I mean, the technique was relatively simple. Yes, what he was doing, he was counting words. Okay, so he was looking at the words in the title of the article, at the words in the article itself, and then, you know, analyzing what it is, you know, what is the diagram in, I mean, what are the words that more often are associated with success of the article in some kind of a, you know, statistical data mining way, okay? And so what was interesting is that he essentially took the stuff from the classical media, okay, like New York Times or Wall Street Journal, but connected it to so-called new media, okay, to social networks, which is Facebook, Twitter, and, you know, and some other stuff. So what is the statistics that's used, okay? So number of likes, number of tweets, yes. The measurement of the topic was essentially by keyword, but there was also, you know, but this gives us also some popularity of different types of words. And another thing that he did is, you know, the measurement of text versus video. And it turns out, you know, one of the surprising corollaries to this study is that people don't always know how to best use the video, okay? So the results are actionable. And actually, I mean, when I first read about this study, yes, and watched the previous version of this video, I sent it to a colleague of mine who works at the New York Times, and he was actually very interested in the study. I mean, for one thing, it showed that New York Times is really the most popular medium, which was, of course, nice, yes. but also because it gives you some way of measuring the impact of what people write. And that is very important because in general, newspapers are not a very profitable business, even if they migrate to the web as, you know, Wall Street Journal, New York Times, or other leading newspapers are doing, okay? Surprisingly, you know, that one story can generate 50% of the impact per day. I mean, in some sense, you're gonna have this kind of a distribution whereas a small number of stories would have disproportionate impact. I mean, that's normal. I mean, that is something to be expected. But the fact that it's 50%, I mean, this is big, yes? Another thing which is interesting is that politics and celebrities are not that important. That people care more about opinion pieces, about, you know, how to do things. So people are not necessarily interested in politics or gossip. User interest decays very fast, probably faster than anybody before this study assumed. And the actionable insight is that you can promote your best story because you can advertise these best stories on other pages of your, you know, of your content on the web. And you can also invest in mining in real time the information from the Twitter, from the, you know, from Facebook, maybe from LinkedIn, for some other media, to decide, you know, what it is that we want to promote and why. So, as I altogether found this application very interesting, very simple language processing technology, very high impact, okay? So as your homework, okay, because we will not have time to do it, I mean, I would like you to listen to this presentation again. Again, you can type in Google Lifshitz or just log-like study, and you're gonna find the URL that has this presentation. And try to sketch the algorithm, that is what it is that's happening in steps. You know, where do you have to go for information and what you do with this information. You don't have to implement anything, but just try to figure out, you know, what are the steps that allow him to come to these conclusions that we just heard. All right, some additional comments. Notice that the value here, okay, the value of this study is in organizing the information. The data is public, yes? I mean, he didn't have to ask New York Times for the permission. The number of likes on Facebook are accessible even through the interface, similarly for Twitter data. Okay, so anyone could have done it. I mean, there is nothing there that is really proprietary, but you know, but there is a big value in what he did, okay? And there is a value for a commercial organization doing a similar thing internally. Again, it shows that, you know, even simple analytics, text analytics, is crucial for organizing data with textual content. So, for instance, in this case, it was also about photo and video descriptions. As we mentioned before, simple techniques can give you powerful results. So now, of course, the question is what happens instead of just looking at, you know, single words, we start looking at 2 words together and 3 words, and are we going to get something more interesting? And the answer is, in general, yes, but it's not going to be sufficient. So I'm not sure if if I should continue. Do you want a break? Shall we go through another example? Okay. So here's another example, okay? In this case, we're going to be looking at pairs of words, all right? This is an example from a different domain, okay, from medicine or some sub-branch of medicine, which is going to be named shortly. And in this case, what we are looking at is 2 words, okay? And we are ignoring stop words like, you know, to, from, was, but we are looking for you know, all other words, okay, in a sentence or a couple of sentences. So here we have, you know, a graph which essentially shows the number of times one word is following some other word. So for instance, here is I woke up, yes? So it appears 11 times in this particular set of sentences. Then we have I walked probably to a place, all right? Then we have here 7 times we have I hugged. Okay, I hugged grandma, okay? So hugged grandma appears, you know, 8 times, and then grandma and strongly appears 9 times. And then after strongly, the next sentence starts with I 10 times. So that's essentially what the graph says, okay? We take these successful words, we put them in a graph, and then we plot this graph like this, okay? So again, a very, very simple application. Anybody could have done it, yes? I mean, is this understandable what's happening? Okay. So now, so with that in mind, this was used as a help in diagnosis, and here what we have, you know, people, you know, the medical practitioner, yes, typically does the interviews. You go to the doctor, and, you know, before any tests are being done on you, the doctor is asked, well, where's the pain, yes, and you point to one point or to another point. The doctor might ask you, do you sleep well? You know, how is your stomach? And a bunch of other things. So here, a similar situation is happening. There is an interview. And from the interview, the doctor can perform a correct diagnosis in 62% of the cases. Now, instead of doing just the interview, yes, I mean, or ignoring the interview, we just take the words from the interview, we divide it into, you know, into segments consisting of a bunch of sentences, and we record, you know, the temporal succession which you saw over there on this previous diagram, yes, here on this diagram. But we also record things, you know, whether they were spoken quickly and about, you know, the distribution of topics. And you're going to see it in a second what we mean by the distribution of topics. So the temporal succession, by the way, I mean, sorry, how quickly they were spoken, yes, oops, going ahead, okay, is also represented here. That is, we are taking, say, 3 minutes of the interview, yes, 3 minutes of text, or, you know, or a minute and a half of text. And of course, if you speak more words in a minute and a half, you're going to see more words, and that's what some of these graphs going to show in a second, all right? So, but the point here is that this new method, again, a very simple method, is 93% accurate. So this could be used to augment the, you know, the accuracy of the traditional diagnosis. Now, what is this diagnosis about? We are talking about the diagnosis of mental disease. So these are psychiatrist interviews, and typically this kind of diagnosis is done by the interviewer, by means of an interview. The tests in terms of, you know, of brain x-rays or that kind of stuff doesn't really apply here. And what you see here is a difference between sort of a normal person pattern and, you know, and a schizophrenic and somebody with a mania, okay? So, I mean, it doesn't matter what really the words are, although, I mean, there is also the difference in the vocabulary here, but you can see the differences in the pattern. So this is, you know, again, a very, very simple application of text analytics, in this case to, you know, in the medical domain. It doesn't require much, but, you know, but it does require seeing certain kind of patterns, and then having tools that would allow you to essentially take the words, maybe do automated transcription, maybe do the transcription by a person. Maybe it really doesn't matter what the words are. And then build a classifier that can sort of suggest sort of the mental state of the patient.
The classifier was built by using what technique?
I actually don't remember right now, but I mean I have a reference here, so if you would like to read the paper, I mean it really doesn't matter. I mean let me. Okay, so the reference is on the next page, but let me just answer the question. I mean, typically what people do when they are building classifiers is that you experiment with many classification methods, yes, and then the one that works best and that has been tested on some unseen data is something that you put in the paper. So, I mean, it is not clear that, say, whatever works for English would work best for Polish. So I really didn't pay that much attention to the kind of classifier that was built here. All right, so here is the whole abstract, which I'm not going to read, but you can just look at it. But I think some points are worth emphasizing that they are trying to extend results. These are initial results reported in April of this year, but in the peer review publication, okay, called Speech Graphs Provide Quantitative Measure of Thought Disorder in Psychosis, yes? Okay, they are trying to sort of also look at other emotional alterations or modalities of thoughts as autism and Asperger's disease. And again, they are looking at words and speech structures revealed by graphs, and maybe they're going to introduce something else. But I thought it was an interesting application that really, I mean, almost anyone could have done. Okay, I mean, it doesn't require much in terms of text analytics, but it does require understanding, of medicine. And actually, the research was done by a combination of computer scientists and medical researchers. So that's, I think that's what we're gonna see, that, the best stuff is gonna happen somewhere on the borders between different disciplines. All right, so let's start this second part. And in this part, we will try to give you some idea about what language processing can and cannot do. That is how good it really is. We will not talk about how these things are done, because some of them are complicated, like this factoid question answering here, which the machines can do, and that was Watson, okay? But we will try to describe how these things are done, or some of these things are done in the course of these lectures. All right, so as you see on the top here, yes, we can do factoid question answering, which is answering questions what, when and who was born where, when was Shakespeare born, or what play did somebody write. But we can automated tutoring, which is about answering questions. How do I do this? Why is it so? Why not do something else? So the machines cannot do that, okay? This requires a different mode of thinking, and as far as I know, it's a completely open problem. People have been trying to do a little bit of work on instruction processing, that is answering the questions, how do I don't know, remove the virus from my computer, how do I assemble a bicycle, that kind of stuff, these kind of descriptions, but really machines cannot do this. We can do automated ad placement, okay? Google does it reasonably well. But say if I want to apply for a job and do it in the automated fashion, yes, that is not possible. So imagine a situation that I have a resume, maybe even several versions of it, and there is a number of job ads, okay, in the United States that is, in some specialties, a relatively common situation, especially before the recession. And I would like the machine essentially to customize my resume, my CV, and send it to the right job for the right reason, and that cannot be done, obviously. We can analyze sentiments, okay? Does somebody like the book or the movie? But we cannot summarize a New York Times discussion. So New York Times is moving to the web, okay? And many of their opinion pieces especially generate a lot of discussion. So you can find, I don't know, 2,000 comments on various economic or intersection of economy and politics for the opinion piece by Krugman, okay, who's a Nobel laureate in economics. I would be interested in reading some of these opinions, but I don't know which one to choose, yes? And there are 2,000 of them. So I certainly am not going to go through 2,000 to find, you know, something that might be of interest to me. And I would like to have a machine that would take into account my knowledge or provide some visual way of summarizing what it is that's happening in this discussion. We can build a machine that can monitor for simple events. So say if I am interested in a certain company, okay, because I want to trade stock, I might be monitoring all news articles about this particular company or about competitors that say announce new products. So new product announcements in the certain domain, we could do it automatically. But say if I own a bunch of patents, yes, I am IBM or Motorola or Microsoft, and I want to understand if some company announcing a product might be infringing on my intellectual property, I do not have a machine that would do so, okay? I really have to ask people to understand what it is that's been announced and match it against my patent portfolio. In medical domain or in bioinformatics, we can find relationships between diseases and various types of chemicals, you know, like drugs and, you know, and genes, proteins. So all that kind of stuff is available in scientific articles, and we can even form certain chains of inference, but we cannot go from there to automated drug design or drug discovery, suggesting some new drugs, because there are just too many of these possible chains of inference, and machines, first of all, cannot find all of them, and second, they cannot prioritize to understand which of them are more promising than the others. And then finally here on this list, we have machine translation, which is good in, you know, if you want to understand the gist, that is, you know, what it is more or less about, maybe you're going to get it, yes? But if you want to, say, translate a product brochure from English, say, to Polish, because you are entering the Polish market, you will probably hire somebody to do so, okay? The best can be done is that some of the brochure can be sort of translated automatically, and then you have a professional translator correcting it, but even that is still rare. And the difference is that these are essentially sort of what we could call, you know, relatively shallow techniques, maybe, you know, except for this factoid question answering, where the depth comes from a huge array of algorithms and machine learning techniques, which is I would say some simulated depth here in case of Watson, but here this requires really understanding what is the content of the message in the text, what it is that the text is about, and what are the relationships between the elements of the text. So this requires some depth, and the computers are not very good at it. To continue this list, search queries on keywords, yes, machines do it very well, but say combine information from multiple sources based on a natural language phrase. So for instance, I don't know if you heard of Wolfram Alpha, which is a search, a kind of search engine, yes? So say I would like to ask a question, I would say, about unemployment rate in Westchester County, which is where I live, north of New York, yes? I cannot do so, okay? The information is there because, they scan all kinds of government databases, but they are unable to do this very simple combination, and even, more complex queries are also not very, neither successful, they are not successful, okay? We can do speech transcription, okay, so essentially dictation of radiology reports, or we can do airline reservation by, by a natural language dialogue. But we cannot do speech to text in a large domain, even, with a very large amount of data. That is, we cannot, say, take a machine to a meeting and correctly transcribe who said what. Okay, that is still not possible. We can do vocabulary, grammar of style assessments. That is, we can actually grade essays, which is quite amazing, okay? That you have an essay written in English and using a combination of grammar checkers and various kinds of statistics, we can actually assign a correct grade to such essays. But we cannot do, again, we cannot do tutoring. We can build a machine that could answer simple math questions, okay, even, sort of the ones that are textually expressed, but again, we don't have a tutor. We can generate diagrams based on certain metadata, but we cannot describe a diagram or search images, okay? And finally here, we cannot pass the Turing test. The Turing test is the machine pretending to be a human. So essentially the test consisting of a situation where, there are some words appearing on a screen, a person or a number of people can engage in a conversation with each of these screens, and then a machine passes a Turing test if, the person after, certain number of turns says, this is a human, and the person is talking about the machine, the judge is talking about the machine, okay? That hasn't happened, and it's not likely it's gonna happen soon. But we can do simple things like order tickets, transfer money from one account to another. This we can all do using language commands. All right, so the next topic is machine translation, okay? And I chose it because it will allow us to go deeper into this idea of counting words, yes? So we had, one count that is, in this first application where we're measuring the impact in social media of various newspaper articles, yes? Then we had these two counts where, we drew graphs of bigrams or two words together to help with medical psychiatric diagnosis. Well, of course, this is going to be about number 3. But also, I mean, 1 and 2 I used, and 5 grams are important. We're going to do it a little bit a detour in the process to show how this kind of n-gram-based methods were used in Watson to help answer some questions, okay? Historically, it's an important topic. Language processing started with the attempt to do machine translation from Russian to English during Cold War. It wasn't, that successful, and the motivation was obvious that very few people in the US spoke Russian. So understanding, Russian documents was important at that time. All right, so, well, here is a Polish text translated into English, and you, of course, will recognize the text, yes? But try to see if you can understand the English here, whether the English seems to be correct. So, I mean, first of all, do you recognize the text? Yes? No? Yes. All right. So, obviously, okay. Well, I mean, I tried to choose something that was known to everybody, or at least it's supposed to be known to everybody, all right? And something that where we can show some of the shortcomings of the current machine translation methods. And then, you know, we're going to see where these shortcomings might be coming from. We don't know exactly where they are coming from because we don't know the exact methods that was used to do this translation, all right? But I did the test because, you know, I wanted to see if this is understandable to a native speaker of English who doesn't know anything about Polish culture, or at least Polish poetry. I mean, Polish culture, maybe that's too strong, but Polish poetry, okay? So I tried it on my wife, who's an American, and my daughter, who's also an American, and they haven't read Mickiewicz either in Polish or in English, and they were able to get the gist about, you know, the about what it is about, you know, some landscape and returning to the homeland and that kind of stuff. So it essentially serves its purpose, okay? Now, if we compare it line by line, we're gonna see that it just doesn't make, a lot of it doesn't make sense. I mean, it's just not good English, yes? I mean, this is just, you know, somewhat absurd, yes? We return to the homeland miracle womb. I don't know, that's definitely not, there is no miracle here mentioned in this phrase, for instance. So, so in general, okay, what you see there is that, you know, the English is not so good, but nevertheless it gives you an idea about what the thing is about. And another thing is, which is interesting, is that, you know, you can find out something about rare words like, you know, dzięcielina pała, yes, okay. So dzięcielina is a type of plant, and here it's, you know, correctly translated into English. I actually checked that, okay, both looking at the Polish Wikipedia and English Wikipedia. So the machines are very good at, you know, at making these kind of choices where sort of rare words are involved. Let's see what else can be said here. Well, this is the translation back, yes? So that is not exactly sounding like Mickiewicz. And there are some very strange errors here, like for instance, here we have this distribution of wyzł, and then acanych comes after pszenica, instead of, you know, wyzłacanych pszenicą. But, you know, as a gist, it's not too bad, and it's actually better if you use a more contemporary text. All right, so here you see the two poems side by side. So, all right. So try it at home. See if it works. See what you notice, okay? And in the meantime, we're gonna progress to something else. All right. Well, that was supposed to be the beginning of lecture number 2, but of course we are a little bit delayed, and that's okay. So, where are we? Okay, well, we just saw machine translation. Okay, similar techniques that we're going to be talking about are used in speech recognition. And actually, these techniques originally come from speech recognition. There was a large group of researchers at IBM working on speech recognition in the 80s and the 90s. And there is still some people doing that. And these algorithms in the paper that we mentioned, and which we more or less going to follow, were originally designed for speech record. Okay. Oh, another thing. Yes.
On machine translation.
Yes.
Parsing trees are involved.
That is a very good question. Okay, they will not be involved in the next 45 minutes. Okay, but actually, what was interesting about this paper, it showed that you can do better machine translation without parsing trees, at least in some parameters. However, modern machine translation, and presumably what you saw before, uses some amount of parsing. We don't know how much, but given that...
Natural language parsing is ambiguous.
Yes, but you can choose, but the machines are pretty good at choosing the right parse using some probabilistic methods, okay? But I mean, the reason I want to talk about this stuff is that we do not have to talk about parsing at the moment, but the methods are important, okay? We used similar methods in Jeopardy, when doing the Jeopardy project, it's essentially sort of part of the common culture, okay? If you do natural language processing, you have to know something about machine learning. You have to know something about, the algorithms that underlie this kind of statistical language processing. This is statistical language processing at its purest. And moreover, there are some very interesting ideas there. So we will try to cover them. And we will also talk about, a little bit about the Bayes theorem, just to refresh your knowledge of probability calculus. Oh, I want to mention, okay, here I have these 3 points so that I don't forget to mention them. What was important about this paper is 3 things. That, the models were non-trivial, but then, many people have proposed interesting non-trivial models of various phenomena, okay? But what happened was that the paper, the research was done at the right time. That is, machines were strong enough at that time to handle enough text that these models could actually be empirically tested, and these people could show that, yes, this method is actually working better, at least with respect to some parameters, than the alternative methods that use, parse trees and traditional linguistics. Moreover, okay, and this was maybe a little bit oversold, they were saying, look, here we don't really need humans, yes, these machines can learn automatically, so therefore if you give them more data, they're gonna perform even better, okay? That was the selling point, and that selling point changed the field of computational linguistics and language processing for about 10 years, where people were trying to throw more data at the machines, use better algorithms, and see how far you can push this statistical paradigm, okay? And they did get some interesting results, but in general, the work has shown that, yes, you probably need to combine both statistics and sort of more traditional structure-based language processing. All right, so here we have two people, okay, and they are both associated with the Bayes theorem. Okay, one of them is Bayes, yes. Who's the other guy, and which one is which? All right, so the other guy is Laplace, who apparently was actually the guy who published it, rediscovered it independently and made some use of it. But this guy, this is Bayes, discovered it first. Okay, so it is called Bayes theorem. All right, so what we need here is a definition. The definition is conditional probability, and it essentially says that, that if we have some event B and this probability is non-zero, because it is defined only for such events, then the conditional probability of A given B is defined as this ratio, okay? So we take the intersection, okay, or the measure of all the common elementary events. And so how much of B is in A, okay? That's the conditional probability. All right, so that's essentially what we need here. So therefore, from this definition, if we want to know that A and B happened, yes, we can multiply by P of B, and we'll have it as P vertical bar B times P of B gives you this thing, yes, this joint event. And that's the only thing we're going to be using, okay? That's not the Bayes theorem, but that's the definition. The Bayes theorem basically says that, okay, we can look at it from two sides, from the B side and from the A side, and combine it, okay? So here we have the Bayes theorem, okay, and its derivation, looking essentially, we decompose A intersect B into two products. Yes, here we see these two products, and then we say, A conditional on B is the same as this particular ratio. And why is it important? Because we will try to predict the future based on what happened in the past. That's essentially what the Bayes theorems allows you to do. And we have the little illustration here from Wikipedia, which is a great resource for all this stuff. All right, so here we have a situation where, we have a very good drug test, okay? Say we test for somebody using, I don't know, alcohol, yes? Or, or some other, or illegal drugs like marijuana. And it is 99% accurate, yes, both in terms of true positives, that is, if someone tells is positive, then it's 99% correct. And the same thing if it says, no, this guy didn't use the drug, then it is also 99% correct. So it's a great test. Very few medical tests are so accurate, actually. And then let's assume that, that, I don't know, say 5%, 0.5% of, I don't know, all drivers use, this either alcohol or this legal drug or some other situation that we want to test people for. And then we ask the question, okay, well, we just got this guy, okay, he tested positive. What are the chances that, and what is the probability that actually, this guy is guilty as charged, all right? So here's the analysis. All right, so basically we use this Bayes theorem and we compute, say if we have, it's best to do it on the example. Yes, we have 1,000 individuals, okay, and there would be about 5 users there. From the non-users, there will be some false positive because the test is not perfect. Yes, that is, about 1% will be falsely accused. And so we can expect, only about 5% out of the 15 positive results that are genuine or that is a true positive. Okay, so this is the math, and you get the chance that that actually the guy is probably more likely to be non-guilty than guilty. Okay, so try using it next time you get stopped, and see if it works. All right, so we're gonna be using this stuff. Okay, so we're gonna be following more or less this paper. All right, and we're going to be trying to translate from French to English, okay? But we're going to be doing in a very weird way, and this is the the genius of the paper, that instead of translating from French to English, we're going to be pretending that English was translated to French, and then we're going to be doing some estimation, some math that would allow us to find the right translation to English, okay? So here you see this English translated to French. All right, so we have this string here, this sentence, il me semble faire le signe que oui, okay? So basically it seems that he said yes. Okay, that's a rough translation. So something about somebody making a sign yes, a positive sign. And we will try to find the corresponding English sentence, okay? And we're gonna do it in the following way. With many detours, okay? So this is gonna be a long story, okay? All right, so essentially we're going to be looking for an English sentence E such that it's most likely that this thing is going to be in balance, okay? It has to be a probable English string, so it has to be something that, say, an English person could actually say. It cannot be a bunch of scrambled English words, all right? So that's what this part says here. And then this part, it will try to find the connection between French and English, but it's doing it backwards, yes? That is, we are trying to look at all possible English sentences, and then we're going to translate them into all possible French sentences, and then, pair them somehow. All right, and maximize this thing that, so any English sentence could be translated here into any French sentence. Of course, for most of them, or at least string, actually we should talk here about not even about sentences, we should be talking about strings here, just strings of words. They don't have to be in order, yes? For most of them, of course, this probability will be 0, something, maybe we don't want to use 0 sometimes, but something very close to 0. But for some of them, it will be more than 0. Yes, especially if some English words are correctly translated into French, and even if the order is scrambled, there is a chance that we will find a document that is a translation of one text to another. That gives you the right words, yes? So they called it the fundamental equation of machine translation, so no modesty there. But it is an interesting idea, yes? We are not trying to do direct translation. Instead of, we're going to look at this huge space and then say, okay, we're gonna do something here in this space, okay, just work with English. And then we're going to look at all these possible combinations and do something about these possible combinations and try to provide some estimates. So for that, you need powerful computers. Yes, you couldn't do it in the 60s or 50s. And it's not how people do it, yes? I mean, say if I want to translate from English to Polish, or to the French or German or Russian, yes, I would try to first express it perhaps in, what it is that this thing is about, and then find appropriate nouns and verbs that express these concepts. But machines don't have any concepts, so this is all done on strings of words, all right? And at that time, the machines were getting strong enough to actually do it. This will be mentioned in a moment, but let me just tell you what was, where the data came from, because they needed data for that, to estimate these probabilities. That it couldn't be just something out of the blue. So they used something which is called the Hansard corpus, which is a translation into French and English. So if somebody spoke in French, it would be translated into the English, and if somebody spoke in English, it would be translated into French. And that was of about, I think, 100-something or 200 years of the Canadian Parliament. Okay, so Canadian parliamentary debates. These were the translations. So there was a reasonable amount of data there. It's not as much as we could get, through Google now or through existing corpora, but in late 80s or early 90s, that was quite a bit. All right, so, well, I'm going to be repeating myself many times, yes? But again, we do not care what this thing means, yes? We're just gonna do it all mechanically, okay? We're gonna check all possible English word sentences, compute their probabilities, and we will compute the chance of generating a French sequence containing these words, okay, in some order. And that's essentially what the method will do, okay? So this is this part, but then, of course, we care about this part too, and this will tell us, which of these sequences actually are well formed. All right, so again, we need estimates of English strings, okay, so this is this part, and then probabilities of generation. This comes from the Hansard corpus, going back and forth. And then, we need some method of computing the maximum. So, I mean, this is just, in a sense, it's a pure math. In the other sense, if you have a lot of data, it's a non-trivial thing to do. But we will not talk about it, definitely not today, maybe in some of the future lectures if we have time. So this first part, okay, the estimation of these probabilities is called the language model. So this is our English model. And this part is the translation model, okay? So this is the vocabulary. All right, so again, building this intuition that we are building the translation from French to English, but we run it, we feed it French and ask what English would have caused this French sentence to come out, okay? So this is weird, all right? And the answer is this, that it has to be a fluent English sentence. That's the first part, and the words might get translated into these other sentence. All right, so why not do it the other way? Because usually we do not have enough data to do to translate directly, okay? Because maybe this is a rare French sentence, okay? It's a long sentence, nobody spoke it before, so it's very difficult to map it directly into an existing English sentence. So that's why they decided to do it the other way. And this part, since this is sequences of words to sequences of words, doesn't have to have a good French translation. We don't care about it if the translation is good, as long as it has the right words, the right phrases, okay? And it can have, it may be, some of them might be bad translation, and this can be sloppy because this part will take care about generating the right English sentence. All right. So that makes, so this is the genius of the method, okay. So the same thing illustrated, yes. So if we were to do directly, we would probably, generate a lot of bad English for novel French sentences, okay. But if we do it the opposite way, we generate a lot of bad French, but we don't care because we're going to be doing only good English. That's the first part. All right. So how do we build a language model? We do it by counting, yes? So, probabilities and counting are related. So, for instance, if we have the, the sentence, it seems to me he's nodding, yes? Basically, we can count the number of nodding followed by it seems to me he is, okay? And this is going to be the same number, yes? So this is where this, conditional probability comes from, yes? So we are counting nodding. We have nodding under the condition that it was preceded by it seems to me he is. And then, we have a synonym, more or less the same meaning. It seems to me he's agreeing, okay? Again, we can count number of agreeing following the it seems to me he is. And then it can be translated not just by one word, but more than one word, like saying yes. So again, we're going to count this number of these phrases, and that's where the conditional probabilities. And in this case, as you notice, we are not dealing with French. There is nothing about French. We are just creating a language model for English. So in principle, it doesn't have to come from the Hansard corpus. It can come from some other place if it would produce better estimates. All right, so now if we have these counts, we can translate them into probabilities, yes? So the probability of seeing it seems to me he's nodding is, based on this formula, yes, the probability of seeing nodding after it seems to me he is times probability of seeing it seems to me he is. And same for the other sentences. For agreeing, yes. So we basically can now translate counts into probabilities, and that's how we get the language model. All right, computers are very good at counting, yes. So, and then, the simplest language model, if we want to, since here we have, some longer strings, yes, these strings can also be decomposed into shorter strings, and then we can just, count words or count bigrams. So this would be the, one of the simplest language models where, we estimate. Now this is the estimate. We estimate the probability of seeing this sentence essentially by the product of, one word following the other and the first word appearing at the beginning of the sentence. All right? So no magic here, just, the application of the Bayes theorem as motivation, and then, a relatively simple estimator. Okay, so the only thing we need here is essentially bigrams and trigrams. Yes, here we have seems to. Okay, so if we want to deal with 3 words, we can deal with 3 words. We could actually do it just with 2 words, but the paper actually showed that for that particular corpus, number 3 was optimal. That is, best estimates were using trigrams. There is a more recent work based, I think, on the Google Ngram collection, which goes until 5, and some other statistical estimates that actually the optimum number of ngrams for, they claim, for general English is 5 or 6, or somewhere between 5 and 6. But at that time, you know, number 3 was the magic. All right, so we're going to digress now. Now we know how to build language models. Yes, we know how to compute, you know, these 1 grams, bigrams, 2 words, or 3 words collections. Well, it turns out that actually these things have some interesting uses. And we used a collection of n-grams going from 1 to 5 in the Watson project, in the Jeopardy project. So I'm going to talk a little bit about that now. And then we're going to go back to translation to focus on the translation model. All right, so how can we apply n-grams? So in Jeopardy, there are these questions called fit B, or fill in the blanks. So there is some element missing here, yes? And the category completes the play title, so it tells you what it is that you have to know. And this is the author, and you are supposed to say, you know, what it is. Is it the great white, what, whale, I don't know, house, fever, you know, anything can go there. So if you know something about it, you know, yes, you can try take the right guess. Of course, the machines have some knowledge, but the knowledge is shallow. And as you're gonna find out maybe tomorrow or the day after, we do not usually try to extract candidate answers from all possible text. So in this case, we are trying to extract answers from n-grams, okay? And I'm gonna show it in a moment. Here's another category where n-grams were applied, double-double. Okay, so here we have classic name for the double promontories in the Strait of Gibraltar is the pillars of this mythic hero. So essentially you are substituting something here. For this part you are substituting some phrase or words that continues the pillars of, okay? So again, here we have 1, 2, 3 words. So if we have, say, 5 grams, we can put another 2 words there, and maybe one of, you know, these continuations will be good. And then another category in Jeopardy is implicit relations, and there, this, you know, one of these game categories is called common bonds, okay? And here you have 3 concepts, okay, feet, eyebrow, and McDonald's, and you are supposed to guess what it is that they have in common, and you have to do it relatively fast. And then you have, you know, another question like that: trout, loose change in your pocket, and compliments. All right. So again, what it is that these 3 concepts have in common. And one of the methods that we used in the system actually applied n-grams, but before we go there, I'll give you the answers, okay? So the title of the play is The Great White Hope. Okay, we here we have the pillars of Hercules, and you know, the common thing between feet, eyebrows, and McDonald's is arches, and this one is a little bit more difficult because there is this expression, fish for compliments, when somebody is looking for praise, okay, or fish for change in your pocket. That's sort of more normal. And trout, of course, is a fish, or you can fish for trouts. So how do we find them? All right, so as you might have guessed, we look for most popular or most probable 5 grams, okay, where we have great, Howard, Suckler, and White. So we take this query essentially, we put it in any order. I mean, it really doesn't matter, but we use the alphabetic order, and we look for n-grams which have these 4 words and then something else. So we find, for instance, Great Hope, Howard Sackler White, okay? So in one case it's a hope. We can find another n-gram which has a play. These are the counts. So this appears 13 times, this appears 16 times. And then altogether we might have, say, around 131 such n-grams, okay? This collection that we used for n-grams wasn't as big, say, as Google n-grams, but it was good enough for us to answer questions. I created these n-grams from about 200 gigabytes of text, and then we deleted the least frequent ones. All right, so once we find these, we have candidates. So we have, hope and play as two candidates. Usually we have more than two. And then what we can do is we do something like we check, we try to test each candidate, and we do it in many possible ways. Here I am listing only one, okay? So for instance, okay, we didn't do it in the game, but we do things which are similar, okay? You can go to, say, Google, yes, and find, how many times how many results, search results, you're going to have for Howard Sackler Great White Hope. And the number is this, 50,000. Okay, what about if this is Great White Play? Okay, that would be the second candidate. Well, you only find 3 results, yes? And what is the total number of Howard Sackler Great White? Well, there is about 180,000 results. Well, obviously, this is a better candidate, yes? So you can, we aggregate these scores using logistic regression, but in this case, you could take, for instance, geometric mean or some other method. Really doesn't matter. I mean, we check in more than one way, so we need some aggregation method. But well, the technique is relatively simple, yes, and it sort of simulates intelligent answers, okay? I mean, obviously, it's all purely mechanical. Nevertheless, with a good collection of n-grams and a good collection of sources to check each candidate answer, you can answer, these puzzles which many people have trouble with, all right? Well, homework. Do the same thing, try to figure out what would happen in the other 2 cases, yes? So how do you get, the pillars of Hercules from this query? And, what would you do about common bonds, feet, eyebrows, and McDonald's? All right. So this is the end of digression, and shall we continue? Yes, all right. So let's start the next one. All right, so where are we? Okay, so what we did was we've seen a couple of simple applications. Yes, social network, counting, medical, Watson scorers. We had, some primer on Bayes theorem. We've seen the creation of a language model in machine translation. On the business side, all right, your historical side, yes, text is becoming important. We can do more and more things, but we still cannot do really intelligent things. We touched on this topic, what really is NLP, how it changed over the last 20 years. You could see from examples that occasionally it's important, and the importance might be growing. And from this statistical machine translation, we learned something interesting, a valuable method of problem decomposition, which is not intuitive, but it actually leverages what computers do best, yes, and which is deal with a large amount of data, count, estimate probabilities. And the other method is sort of using n-gram-based models, because they allow us to do not only machine translation, but also some interesting things in the game of Jeopardy. So what are we gonna do now? We're gonna continue with machine translation, okay? So we're gonna talk about the translation model. So probability that a random English string generates a random French string, and how we're gonna estimate it. So that's the translation model. All right, so let's go through that. All right, so you saw this, that instead of doing one way, we're gonna do it the other way. All right. So what is the simplest translation model? Well, the same thing as with the simplest language model. Essentially, we're gonna do the product of individual translations of words, yes? What are the chances? So in order to estimate that, you know, that this generates that, you know, so English generates French, we're just gonna ask, you know, what are the chances that it generates il, it generates me, or me in this case, sorry, or it generates faire, and then, you know, me generates me, he generates il. So all these combinations here, yes? I mean, if we just were to talk about, you know, sort of intuitively, for most of these numbers should be zeros, yes? Because after all, you know, the meaning of these words is completely different, yes? There is no relationship between nodding and sample, yes? I mean, these are different words, different meanings. So this product should be zero, but as it happens, it doesn't have to be. Now imagine a situation that we take, you know, say the whole corpus, yes? In the whole corpus, this probability would be 1, yes? Because of course, you know, this English sentence is taken from the corpus, you know, from the English part, and this sentence appears in the other part, so therefore, you know, all of the, you know, the corpus actually generates all of these, yes? Because we have only one document in the corpus. This is the huge, huge, you know, or two documents, one English, one French, okay? Not very interesting, yes? But nevertheless, non-zero. That's the only point I make. So what is the trick? The trick is not to think about meanings, but find, you know, enough context that would allow us to have a non-zero probabilities here. Nevertheless, you know, they would be relatively small, so the information would allow us to, you know, to find some correspondence between these, so that this probability is non-zero, non-1, somewhere, you know, somewhere in between, and it is generated from the right data. And we do have such data, yes, because we know, what do we know? We know that each speech was translated into the same speech, yes, in just another language. We know that more or less each paragraph is translated into the paragraph. And even on the sentence level, we know that, you know, the sentences are approximately translated. So therefore, we know a little bit more than just that, you know, that we have a corpus. If we try to align these sentences, these paragraphs, speeches, paragraphs, sentences, then from this information, we might be able to estimate the right probabilities. And that's essentially is what's happening, but we go with this alignment a little bit deeper than the sentence, okay? Because sentences, you know, are long, and sometimes the boundaries change, and not every sentence is aligned with the other sentence. So therefore, I mean, what's happening in this story is that essentially the trigrams are being used, okay? So, well, this slide just summarized the points that I made, which, you know, with large enough documents, probabilities are non-zero. We can do better by aligning sentences and chunks of sentences. So for instance, if we can align me semble with seems to me and seem que oui with is nodding, yes, then you know, that we can do even better. And these are the trigrams. Okay, so this is a bigram, this is a trigram. So essentially, if we can sort of anchor these on high probability alignments of trigrams, then this would allow this method work. Okay. In addition, of course, what's happening is that, you know, that the words, I mean, do not necessarily have to appear in the same order. So we allow, you know, he and il to be separated by other words, by some number x of words, and with decreasing probability. So they cannot be, you know, too far, but in the corpus, but they can be separate. The translations can be separated, and then in some cases we do not have the, you know, it is not that always 3 in English aligns with 3 in French. So we have to allow for, you know, correspondences between trigrams and bigrams and sometimes unigrams. And if we augment this model, we're gonna do much better. So that's essentially is the story of the language model. Sometimes, I mean, there are these concepts introduced. So this, you know, allowing one word corresponding to 0 through n words is called a fertility parameter. And, you know, and we also have, you know, this displacement that one word can jump, say, from the end of the English phrase to the beginning of French phrase or vice versa. So this is what the paper discussed. The paper had a collection of models, and, you know, the results were improving with the addition of these new parameters. All right, now the data that was used, as I mentioned, is the Hansard corpus, so almost 200 years, French and English, only 100 million words, okay, so about, you know, million plus sentences. This is not that much, yes, I mean, you know, Wikipedia definitely has much more than that, because Wikipedia, if I remember correctly, has, you know, on the order of 4 million entries in English Wikipedia, maybe more than that. So that is small. Okay, that was on tapes, and the corresponding sentences were not marked, so they had a problem with alignment, but that is not, you know, that is important, but it's not of concern to us right now. So how did they do? This system was called Candide, okay? And we have these two measures, you know, one is adequacy, which is the rating, how much information is transferred. So you want, you know, all information to be transferred. And fluency, whether, you know, the produced language is good. And they were doing very well on fluency compared to the grammar-based translator, okay? I mean, the 4 points is usually quite a bit in this space. They were doing not so good on information transmission, okay? And for comparison, people don't always do that well either. People are not 100%, yes. But the point was also that, you know, that these results were improving very fast with every year, and that was also the strength of the model. It's very difficult to modify handwritten grammars. It was relatively easier to add more data, and with more data and, you know, better statistical methods, the system improved fast. All right, so here are some examples. So we have, you know, this is not possible, okay. Trigram said impossibility. Well, that's close enough, okay. The parser would say this is impossible, okay. So all three are still, I mean, a reasonable translation, okay. Here we have, this is the globalization of production. The parser-based translator would say this is globalization of production, which is, I mean, is just missing the determiner, yes. So the meaning is more or less the same, and the trigram says this globalization of production, so it's missing the is. So this is reasonable. And there are some of them which are not so good, okay. He said he often eats Chinese dishes, so basically, eating Chinese food. And the trigram said, he said China frequently tastes food, okay. So this is that, I mean, it's not even just translation, this completely misrepresents the meaning, yes. And the parser, he said recurrent taste of Chinese cuisine, okay. Well, I don't know, there is something here, but but this is a funny way of expressing a simple thought, yes. Wishful thinking, out of touch with reality, and trigram, divorce practical delusion. Well, that's great haiku, I would say, yes. I mean, if you think about it, it's quite poetic. And parser is more or less in the same vein, but I think this actually sounds better. All right. So, well, this is the summary. All right. Again, the trick was any English into any French, but some translations are more likely. We can anchor it on phrases essentially, and then we maximize this product, and we will not talk about maximization now because we have some other things to cover. Okay, so what is the conclusion? As you saw in this table, in some categories the traditional grammar-based techniques did better than Candide, and so many people concluded at that time, myself included, that we need a combination of these techniques. Nevertheless, for the next 10 years, I mean, things were mostly done by statistical techniques, and a lot of effort went into improving machine learning for NLP with great results, great algorithms, so it wasn't a wasted effort. However, when it comes to translation, from what I know, and I'm not a specialist in translation, but from what I could read and talk to people, that currently people do use the combinations, that is, they use statistical method with a lot of data, but they try to anchor it not just on words, but on parsed phrases, and this basically leverages the structure of the language. And in general, okay, especially say to answer the Jeopardy question, you need the knowledge of the world. You have to know, in some sense, you have to have somewhere encoded that this was the author and that was the name of the play. All right, so we can't avoid it. So we will be talking about the structure of the language and the knowledge of the world a little bit before going to before talking about the Watson architecture and Watson natural language processing. So what is the linguistic model, okay, that people originally proposed for machine translation was something like this, that you have the text and then you do some analysis which could be quite deep. You have some language of thought or some other semi-formal logical language which was called interlingua. There is no, there was no one proposal about what it would be. So it could be logic, it could be something else. Actually, I mean, some people seriously proposed Esperanto as interlingua, okay, all right, but I think sort of logic-based proposals with some additional structures were more common. And then once you analyze your original text, you would then somehow do generation, so you generate from the combination of syntactic and semantic features, so knowledge about the meaning and knowledge about the structure, you would generate the new text. Say, if this was English, this could be French. If this was French, this would be English. What the statistical methods that we talked about did, they essentially did this direct translation, okay? With a lot of data, it just mapped from one language to another, really without discovering any explicit grammatical structures, yes? And somewhere in between, people are doing translation using grammars. That is, you have English grammar, you don't look for meaning, but you also have a in parallel developed, say, German grammar, and then you do the map between different grammatical structures. So many commercial translation machines work actually, somewhere on this level. All right, and to do so, you need all this knowledge about, the language, that is how words are put together from pieces, yes? That's very important for Polish, yes? Where you have, preposition, postpositions. It's less important of English, where all of these is in separate words. Then how phrases are put together, so where are the boundaries between noun phrases and verb phrases, so these are called chunks. How do we put, predicates and arguments together in some kind of a syntactic parse tree. Okay, we will be talking about that, different methods for doing so, and this is the topic of parsing. Then we talk about meaning, because really, if you want to do proper translation, you have to somehow represent the meaning of the sentences. And finally, the context, okay? I mean, is it formal, is it informal use? The same words have different meanings depending on this kind of contextual parameters. All right, so this is important for machine translation, but I think at this point we're probably going to close the topic of translation. So why am I mentioning this? Because essentially the same model is important for doing Jeopardy, for building Watson. Okay, we do need methods for doing some language analysis, finding chunks, parsing, of course you need morphology to do that, and you need some world knowledge, some semantics, predicate argument structure, and then there is the knowledge of the game, the knowledge of what it is that the answers might look like. So this is the simple, relatively simple pragmatics of the game. Say, just to mention pragmatics, as you might know, the team I am part of, okay, the Watson team, we work on applying similar technologies to medical domain, yes, as a help in diagnosis, for instance. And there, the pragmatics is actually quite complex, and at this point, I don't think we really have a good handle on it. So there is a lot of open problems. Essentially, from here down, I would say that the field as is doesn't have good solutions, okay, very reliable methods. All right? This way, at least when it comes to English, doing sort of simple morphology, English morphology, dividing, finding noun phrases, this is very reliable, high 90s and very, very few errors. So parsing is somewhere in between. We are doing here, depending how you count, between, say, high 80s and mid 90s correct. Semantics, I would say, is a completely open field, and pragmatics, people only deal when they have to. So there are some general maxims which we will cover, but not enough formal work. Okay. So, is it all about counting? Well, we already know that it's not, that we have to deal with the structure of the language, but we can do quite a bit with n-grams and probabilities. So, could we do Watson only with counting? And obviously the answer is no. And what we need is language, knowing something about the structure of the language, okay? And there is more than one model for this structure. We're going to cover some of them, okay? And the basics are that, that there are nouns, verbs, adjectives, other parts of speech, but how they are put together and, and what's most important, is it top-down, bottom-up, all that kind of stuff is still being debated. Most people agree that there is a phrase structure, that is, there is, something about a noun connected with the adjective, all right, and that's one unit, and we call it a phrase. Okay, verb phrases are sort of more problematic, but we still do it because it's useful to go from a verb to a predicate when trying to represent a meaning. There is no agreement what meaning means, but we are trying to represent it nevertheless. Okay, and then finally, okay, you know, language has structure, but also knowledge has structure. Text is about something. Okay, we're gonna see. I'm gonna be talking quite a bit about preparation of textual resources. Okay, so for instance, you know that, say, and then a Wikipedia article is about the thing that's in the title of the Wikipedia article. It's also about some other things, but it's mainly about this title, and that's the fact that that's going to be used by Watson. And in addition, you know, you can do some representation of semantic network. Yes, that certain predicates have certain arguments. Yes, we can have a database listing, say, all the winners of various medals in all Olympic disciplines. Yes, and essentially represent it either as a big table or as a graph, and also use it to answer questions. So there is quite a bit to the knowledge structure that is of interest to us. All right, so well, this is, you know, one of the official Watson slides. Okay, it shows the sort of I mean, it's the final picture. Maybe not the final, but the final official picture of the game. So here we have Ken Jennings, Brad Rutter, and Watson, you know, represented by this blinking screen. Okay, the machine was actually in the room somewhere, connected by cables, so it wasn't on the stage. It wasn't small enough, but say, I don't know, in 10 years you could probably have an equivalent machine on the stage. This is the amount of money that each of the participants won in the game. So clearly Watson won here. And, you know, and this is the final prize. And of course, you know, Watson's money went to some charities, to 2 charities. And similarly, half of each participant's money went to their charities. But that's, you know, that's the content of the picture and the numbers, but what we care about is that indeed it was a milestone in the AI challenge of answering questions about anything, not about a particular topic where you can build a special purpose machine, but in principle you answer a question about any topic, okay, any topic people can converse about, yes? You know, at least people who read New York Times, Wall Street Journal, and some encyclopedias and like puzzles. So, so definitely what we built was better than what existed before, but it didn't solve the long-standing problem of building the machine that really understands text, and we're going to get to it in a moment. But I want to give you sort of a flavor of what's happening, or what was happening in the background, you know, behind the screen, or, you know, on the other end of the cables. Right? So what you see here is a picture of the Watson architecture, and I think it will be difficult to find here something that says, here we have a natural language processing module, okay? Instead you see all these modules named differently, okay? So let me explain what's happening, okay? There is a pipeline that starts with a question, okay? The question, you know, when the question appears, something happens to the question, okay? And we're gonna go through this. And then at the end, we get an answer, so that's there, okay? We get an answer, and moreover, the answer comes with a number between 0 and 1, and that's confidence, okay? And if the confidence, I think we used 0.7, so if you are, 0.7 or higher confident, we answered the questions. If it was less than 0.7, we didn't unless the machine had to answer. There are some categories in Jeopardy where the machine has to answer questions, okay? So, so that's sort of the main pipeline. And what do we have here? Okay, before we go through the boxes, okay, let me just point to these two things. Yes, so here we have answer sources, and here we have evidence sources. And these are essentially collection of texts, okay? They were processed a little bit, okay, and sometimes quite a bit, but they are the source of knowledge. So everything basically starts with a question, and the question goes after some operations to a search engine, and the search engine tries to find documents that talk about the entities in the question. So if we had, this question about Howard Sackler, and a play, well, it would still go to the search engine, and it would probably go to, it would retrieve the Wikipedia article about Howard Sackler, yes? So, and a bunch of other, we had other encyclopedic sources. We had also books which were not encyclopedias. We had Bible, for instance. We have a bunch of English dictionaries. So there were quite a bit of different kinds of sources. We also had some database-like sources that that would say list the winners of Olympic medals in various years. Okay, so all of that stuff is here. All right. So what happens then? Well, we have to generate a candidate answer. Okay, so from this search we generate the candidate answer. How do we do that? The basic algorithm is very simple. We go to the search engine, okay, and if the search engine if the question asks, about, the third president of the United States that was assassinated, okay, well, we have this in the query, we have United States president and assassinate, and we would retrieve all the documents, or top 200 documents that have these words there, and that are deemed good answers according to the search engine. And we would take the title of the document as the answer. Okay, so Kennedy would be an answer. Yes, McKinley would be an answer. Lincoln would be an answer. But but the point is that that not all of these answers are good, but they all mention the words or concepts that appear in the query. So we get quite a bit of some nonsensical stuff. We're probably gonna get Dallas as the answer, yes, because that's where Kennedy was assassinated, and this fact is mentioned in the Wikipedia article on Dallas, and we're gonna get many other. We're gonna maybe get something from, I don't know, the New York Times corpus, yes, mentioning, which might have a title which doesn't mention any people or entity or anything like that. So we're gonna get hundreds of these possible candidate answers, all right? So what's happening next? Well, now we have these answers, we have the query, so we have to decide, okay, which of these answers is possibly good. And what's happening next is that we score each of the answers. We retrieve the evidence, and then we score each piece of evidence for every answer. So how do we do that? Okay, the basic piece of evidence, again, is going to be text. So what's happening is, now that we have the candidate answer and the query, we put it together, all right? And we do another search, all right? And we retrieve documents which now mention these four things, yes? Say, McKinley assassinate President USA, or United States. And we get, this time we're gonna get, maybe 10,000 documents, okay? Thousands of documents or fragments of documents. And then on each of these fragments of documents we're gonna now look for certain relations. For instance, we'll try to match the relation of assassinate, okay, and then maybe we're gonna look, oh, sorry, there was a numeral third, yes? So something that mentioned number 3, and then there are dozens of such algorithms that would score it. One of them, for instance, will be this n-gram scorer that we mentioned. And so each of these scorers generates some number, and these numbers are put together, okay, by the system that was trained on previous answers, okay, on previously disclosed collection of answers. So this machine learning learned how to put these things together. That is it more important that all these concepts appear in one Wikipedia article, or is it more important that they appear together as an n-gram? And it might depend on the type of the question. Say for common bonds, n-grams are more important. For factual questions, they are less important, okay? So all of this happens here, and here the answer is delivered. So it should be animated now. All right, so in the animation, this looks more or less like this, yes? So we have a question with multiple interpretations, hundreds of possible answers, okay, in many, many sources, thousands of pieces of evidence, and then all of this stuff is combined. So you see here there is little, natural language is hidden. Yes, natural language processing appears in question analysis, and then it appears in how we processed these sources that generate evidence. Some of it actually appears also here. I will be talking about it. And then, a lot of it is embodied in the algorithms that provide scores, all right? So that's essentially what happens. There isn't one natural language processing module that does the understanding and then, matches the question with the answer. It's a machinery that essentially weighs evidence for and against hundreds of answers. All right, so that's what Jeopardy competition did, the system did in the Jeopardy competition. We're gonna cover some aspects of it, but all right, but we have this thing that, that on one hand we are answering question in unrestricted domain, on the other hand, okay, and here's what we could read in the October of last year, it was just after the Lebner competition, which I think happens every other year, if I remember. And in these cases, there are 4 chatbots which were finalists, and they were trying to pass the Turing test, that is, pretend that they were humans, okay? So people have been trying to build these intelligent chatbots for years, and and there are judges that sit at computer terminals. They decide, is it a human or not? And the funny thing is that it only takes 3 or 4 lines of chat. So essentially, 1, 2 lines, 1 or 2 exchanges, and it is clear that the machine, on the other side is not a human. I mean, that it has no sign of human behavior, of human intelligence. And why is it so? All right, so we need to answer some questions, and that's why we have these lectures, okay? So some questions are, what it is that made Watson successful, okay? And we're gonna speculate a little bit on that. We're also gonna speculate why it is difficult to pass the Turing test, okay? So we will need to talk about dialogue at some point, where these dialogues fails. But even, these imperfect dialogues can allow for some intelligent applications, and some of them I built a few years ago. We could speculate a little bit on that. Okay, I mentioned medical. But in general, I think we are still very, very far away, you know, behind some huge mountains when it comes to real language understanding and passing the Turing test. So we're going to answer these later. So to finish today, I just want to touch on a couple of things, and this is going to be preparation for tomorrow, where we're going to go a little bit deeper into some of these traditional language processing topics. All right, so in general, people agree that, you know, that this is a good metaphor for language processing, that we have a collection of texts or collection of documents. We call it a corpus. This is usually a data for us. Then, you know, we have some dialogue or dialogue task, which is a task. So, you know, making an airline reservation or pretending to be a human, yes. And on a still lower granularity, you know, these pieces of dialogue or pieces of document consists of sentences or paragraphs. And there we care about things like, is it true or false? What are the relations? Okay, is it about assassination? Is it about, you know, writing a play? We also care about, you know, grammaticality, at least traditionally, you know, that's what linguists care about. And then, you know, sentences consist of chunks and words, and we care about what part of speech they are, because, you know, part of speech on some level determines meanings. And then, well, often we have, you know, sound in dialogue, but we will not be talking about sound. So this is a natural model, and you know, that's how people think. But it's not always the best model to build all applications, and people disagree whether, you know, this is the answer to natural language processing. And there is a strong, or I wouldn't say, well, strong, maybe it's too strong a word, but there is a growing movement around, you know, building construction grammars where these things are intertwined. There is no clear separation between the levels. So what do we do? I mean, what are the operations that we can do on this model? So of course, I mean, if we have a corpus, we saw that we can, you know, perform some analysis usually by counting. In the dialogue, we usually have some model of what the task is, and we maintain the state, okay? The state is, do I have all the information, okay, to perform the operation, like transfer money or make a reservation? Do I know the account number, yes? Do I know the account number or name of the other account to which I transfer money? Do I have the amount of money? In the airline reservation, you know, the departure time, date, airline, I mean, airline is usually given, but city, do I need to know about the return stuff? Okay, so this all is in the state management. In buying stuff, yes, okay, here's the choice of the book, or, you know, some other a piece of clothing I am buying from Amazon. Yes, there is a state maintained there. Okay, I have chosen, you know, the book, but I haven't chosen the supplier yet. Yes, I might order it from, you know, from somebody who's selling it. So all of that is in this state management. And then in the paragraph where we care about finding relations, truth, grammaticality, yes, what we do is we find a structure, and that's called parsing, and then we try to associate some meaning with the parse, and with the idea being that representation of meaning allows us to do some reasoning, okay? You know, if all people are mortal and Socrates is a man, then Socrates is mortal, yes? So that would be something that we want to represent, but we have to somehow go from this natural language to some logical representation, and then perform this logical syllogistical inference. And for words, I mean, basically what we do is we find the part of speech and then some features. Is it plural or singular? Because that is important in representing meaning. All right. So okay, so now that was this abstract model that we often use, yes? And now here's the concrete model, okay? What it is that went into Watson natural language processing. So what you see here is English slot grammar parser. This is a rule-based grammar and parser, okay, developed over many years, probably about 30 years or close to 30 years, by an IBM researcher called, whose name is Michael McCord, okay? It's the best existing parser, okay? I mean, we checked that, other people checked that. So this is the funny thing, that despite, you know, sort of the huge progress in statistical parsing, this still is the best existing parser, okay? So the structure of language is indeed important. But look, it's 30 person years of development. Not everybody can do it, yes? So, and you can, you know, you can build a grammar which is, say, 10% worse than this with much, much order of magnitude less effort using a combination of linguistic and statistical techniques. But it is currently still the best parser. All right, after we do that, well, we assign some simplified parse which roughly represents semantics. Okay, we're gonna see some examples of that, but you know, it's very, very primitive semantics. You couldn't do the inference on it. And that's also done by the extension of this grammar. We do rule-based named entity recognition. Okay, so we find certain types of entities, not all of them. So we find, if I remember correctly, about 40 of those. So these include people, places, amounts of money, maybe some of the physical units. Okay. We do intra-paragraph anaphora resolution. So you have a paragraph of text, and there, you know, say, I don't know, McKinley is mentioned, and then there are some references to he, him, it, okay, and in one case it can refer to the person, in another case maybe it refers to the mountain, okay, because within the same paragraph we can talk about both the president and maybe the mountain named for him. So we need to resolve some of these references to know, say, you know, that it's the height of the mountain named McKinley that we care about, or the years of the president McKinley that he was in office. So that's what's happening here. Temporal normalization, this is important because the text might say 400 years earlier, yes, and you're gonna see such examples. So we have to know 400 years starting when, 400 years later. You know, how do we do that? So this would be temporal arithmetic. Sorry, temporal normalization about something else. We can say, you know, January 15th or 15th of January, yes? We can say 2008 or 08, yes? There are these different ways of expressing dates. So this dates, hours, minutes, years, all that kind of stuff would be in the temporal normalization. We try to find certain semantic relations, and we are doing it both using patterns and we are using some, you know, some statistical methods. So both of these are being used. So as you see, this has no resemblance to this, you know, typical model. It's just, you know, the typical model would have maybe some of this. Okay, this is all addition, and it doesn't show all semantics. It, you know, sort of represents a little bit of semantics. All right, so parsing. So I'm going to cover a little bit of parsing and then we're going to stop. So what is parsing? Parsing is the assignment of structure to the sentence, and very often it's represented in a tree. Okay, these trees grow downwards. All right. So what we have here is a sentence, say John hits the ball or John hit the ball. We don't know whether it's, you know, whether it's been sort of, whether we ignored the number here or whether it's past. But in any case, we have this initial assignment of noun, verb, and determiner, yes? So we know that John is most likely a noun, and therefore we can form a noun phrase out of this. It's a short phrase, has just one word. Here we have a longer phrase. Ball is also a noun, and the is a determiner. Putting them together, we get a phrase, a noun phrase, which covers the ball, two words, yes? We know that hit is a verb, and very often we attach one of the arguments, and usually not the subject, the object of the verb, to the verb like this, and it forms a verb phrase. This is called the head of the verb phrase, okay? So here we have a verb phrase consisting of 3 words, and this particular features representing, you know, this is the span from covering these letters, this is the span covering this part of the string, and when we put it together we get a sentence, and that's usually represented with an S. And why do we do that? Because basically we want to go from this verb to the predicate, and you know, from this subject to the first argument, and then from the object to the second argument, because the idea is that maybe we can reason about this thing, maybe we can answer a question, you know, what did John hit, or you know, or who hit the ball, and that would be the answering questions. That's not how Watson does it, but that is the traditional way of looking at question answering. Similarly, this is how we would go and do machine translation in the traditional translation model, okay? We would find the sparse, we would represent the meaning, then we would sort of represent a similar, you know, or identical meaning in another language, be it French, German, Polish, or Italian, or Chinese, and then from this we would generate this kind of parse tree, and then finally generate the string in the other language. So what do we need to do the parse, okay, to create this parse? Well, we need a dictionary. We have to know that this possibly is a noun and a proper noun. We need some collection of rules which would tell us that if we have a verb followed by a noun phrase, that they should be put together like this, and not, for instance, this verb with John. So John hit is not a verb phrase in this case. If there was a period afterwards, it would be, I mean, well, it wouldn't be, it would be, well, sorry. In some cases, in some analysis, it would be a verb phrase. In other cases, it wouldn't, depending on which grammatical formula you subscribe to. But it wouldn't have, definitely it wouldn't have this part if there was a period here, yes? So a verb phrase would look differently. So we need collection of rules of putting these things together. Very often we need collection of examples, yes? I mean, in principle, you could write a grammar without any collection of examples because, well, you have the image of how a language works, so you would just create a bunch of rules like this and hope that it would work. In practice, it doesn't work that way. You need your examples to test if you have, for instance, if you made changes to your grammar where your old examples still work, all right? And you need it also for creation of statistical rules, okay? And and statistical inference. So if you want to build sort of a statistics-based...
Statistical rules.
Yes.
It is the tool for choosing of one of several possible parse trees.
Yes. Yes, or phrases. So, so say this would be assigned, as a verb phrase with probability 0.9 based on some probabilities of connecting the ball and making it into a noun phrase, yes? Because there are constructions where, where sort of you can have the determiner, but what happens afterwards is not a noun, like so sort of the more you smile, the more you laugh, okay? So you have the more, yes? So this is a construction where you don't have noun phrases, but you still have the determiner. If the machine hasn't seen this kind of stuff before, it wouldn't know what to do with it. It could still assign it, maybe with lower probability, a noun phrase reading, okay? And then we would get some, some weird parses. But it would warn us that since we don't see a noun there, therefore the probability of creating a noun phrase would probably be lower. All right, so we need examples, both for rule-based and statistical grammar creation. And before we even start parsing, yes, we need to understand whether it's plural or singular, whether it's present tense or past tense. So we need some morphological analyzer and chunker. Okay, so very often we put, say, the titles of books together, okay, as one chunk because we don't want to parse them. It's just a string. It's the name of the book. All right, so what is the problem with parsing? Well, parsing is often ambiguous, okay? Language encodes meaning in a very efficient way. It encodes the meaning so that it can be efficiently transmitted to another human, okay? Not to the machine. So humans have all this common sense knowledge. They have knowledge of language, and therefore they can discard most of the stupid possibilities, okay, very, very fast. However, machines can't, or at least not so easily. So here we have, a sentence, time flies like an arrow, okay? There is a Wikipedia article on this sentence, so you can actually read about it in Wikipedia. People, people have been talking about this sentence for many, many years prior, the existence of Wikipedia. And basically the reason for that is that that you can find at least, I don't know, I think 17 was the number I came up many years ago when I started working in this field, okay, of different interpretations of this very simple sentence, okay? And some of the interpretations are there where you use like, okay, not as a comparison, but as a verb. So fruit flies like a banana, yes? Okay, that makes perfect sense, yes? Okay, so, I mean, the structure is identical, but the meaning is different, yes? And the only thing we changed is the adjective here, yes? Oh, and we replaced one noun with the other noun, right? So very, very simple change. And of course, the machine doesn't know the difference between an arrow and a banana. So one interpretation or the other might be equally likely. All right, so fly can be a verb. That's what we care about. Now, time can also be a verb, and then we have an imperative, yes? You should time your flies like you timed your arrow, yes? You can time how fast the arrow goes from one point to another, all right? And then, if you do some biological experiment, yes, you maybe give some drug to fruit flies, and then you can time your flies the same way as you timed your arrow going, you know, from one corner of the room to another. I mean, it's it's a stretched interpretation, but of course, in some context, it makes perfect sense. And then, you know, are these, okay, is this a verb? Or maybe these are time flies. We have fruit flies, okay? We can have black flies, yes? We can have time flies, why not? All right, you know, a new species of flies, time flies, all right? Then time can refer, for instance, to Time magazine, all right? So we can find many other such ambiguities here. So the point is, it's not easy, okay? And now imagine that now you have a paragraph of text or a Wikipedia document, yes? If you know, every, 5 words generates, say, 20 possible interpretations, yes? Then you have 1,000 words, say, in a Wikipedia article. Well, how many interpretations can we get out of this article? Quite a few, yes? Huge number, certainly bigger than the number of atoms in the universe. So we will have to prune, okay? And we can prune using rules, but in many cases we do have to provide multiple parses. And very often it's not a problem because we can represent such multiple interpretation relatively succinctly, not always. All right, so here's what the ESG parser does, since we are talking about some of the Watson technologies. All right, so here we have a sentence. Can anybody read this sentence? It goes like this. Okay, so she sing a song of sixpence. Okay, that's basically what it is. She sang a song of sixpence. All right, so what we have here is, you know, the verb sing in one case is, sing in one case is a verb, yes, and this is the top predicate, yes. And then here we have a title of a song, and this is interpreted essentially as a proper noun, okay, and a chunk, okay, yes, we have CHN, yes. And then in addition, because sometimes we do care about the meaning of this chunk, this is also interpreted, it's provided an internal structure. So we have, you know, one structure here and then additional structure hidden underneath, okay, that essentially parses this as a separate sentence. So we have, what do we say? Want to say that it has both shallow and deep structure. It can do partial parsing. It does some of the named entity recognition, not all of it, but the stuff that can be gotten from looking at the capital letters and the rest of the parse. So if it makes sense grammatically that this should be one chunk, it will assign it as one chunk and determine that because of the capitalization, it is a proper noun. So that's the morphology part, the capital letters. So now let's see. Okay, so what you see here is the results of testing this parser against other leading parser. And we can see that, for instance, when we do it on the Jeopardy corpus, we are about 10% better. And this was out of the box, okay? So 84%, it was about 1% better. It was about 3% better on Wikipedia out of the box in the course of, of improvements that were produced for the competition. Michael McCord improved it additionally, 3%, and that took a lot of effort. And it was easier on the Jeopardy corpus because there is a specific way of expressing the questions. It's still not perfect, yes, but it's better than any alternative at this point. Okay, so then we need to cover lexicon and grammars, but I don't think we're going to do it today. So let's summarize the day. All right, so we talked, on a high level about the importance of language processing and the fact that despite, big progress, language understanding is still an unsolved problem. Still, even simple methods when applied correctly can give us interesting applications. So we saw, something using bigrams for medical diagnosis. We saw unigrams for determining the impact of articles, yes? And then, we talked about trigrams and how they allow us to create a pretty good model for statistical machine translation, okay? So the main point behind this statistical machine translation is that very often the methods that work best for machines are non-intuitive, okay? Machines should use their strengths, which is counting, being able to aggregate huge amount of information very fast, yes? They do not necessarily have to operate the way we imagine that humans operate. We really don't know exactly how humans operate, but we have some mental models of it. So we should follow essentially the data, and very often that's the best way to build an application. See what data you have and what you can get out of the data. So neither this statistical MT model, which we covered, where we sort of decomposed into the language model and translation model, and the translation model was backward, yes? They are, it's not the way humans would do the translation. And similarly, the Watson architecture, given its complexity, yes, it doesn't exactly look like anything, that you can say I would do to answer questions. Yes, maybe I would try to retrieve some particular pieces of information from something that resembles encyclopedia in my brain, but I wouldn't generate, hundreds of candidate answers, at least not consciously, and then, find evidence for and against for all of them, and then, do some strange model, use some strange model for scoring. So don't worry if it's not necessarily intuitive. Okay, it still might, it might be interesting. We might learn something from it, or at least we're gonna, uncover the next mountain to conquer. And then we only started talking about it, but given this hierarchical model of language, yes, we're gonna focus quite a bit of attention on parsing, that is assignment of the structure to sentences. Okay, that is the key operation in language understanding. So we will need to talk more about it, and then once we have at least some basic knowledge of parsing, we can then discuss how language processing was done in Watson, which will be, which will take us probably about 2 hours. All right, so I think that will be it for the day. So thank you very much, and I will see you tomorrow.